Okay, let's wait for a few minutes. Let's see how many joins. Yeah, hi, am I audible? Yeah, can you please just type something if I'm audible or not?
Audible and the screen visible.
Yeah, okay, thank you. So we will wait for 1 or 2 minutes more and let's see if anyone else joins, else we'll start.
Okay.
Yeah, okay, let's start. So, hello everyone, my name is Rajan Mukherjee and I'll be taking this live session for NPTEL course on reinforcement learning. I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur, and I will basically the flow will be same. We'll be having a recap of what was taught this week, and we'll be solving some sample questions, which is sort of a tutorial. Feel free to ask any question whenever you want, and the session is being recorded, so you can watch it later on YouTube. Thank you for joining. Okay, week 8. So far, we have come across all techniques like dynamic programming, Monte Carlo, TD0, TD lambda to solve all were used to basically solve the same problem of MDP, right? We're using all of this technique to solve MDP, and each one of has its own pros and cons. We have discussed in details. So one thing that is common for all of them was that each state. So there are so MDP problems has basically two things. One was your value function. Another was action value function. Oh, this can be state value function, action value function. Right. So one was your V, another was your Q. Right. So so if you look at each of these algorithms, uh, each of these algorithm has one specific thing that we are trying to do in each time, where we are trying to store the values we were trying to store the values of each state, right? We are basically trying to store the value of each state. So if you remember, we are just doing this kind of stuff, right? D is equal to V plus alpha delta V, this kind of stuff you are doing, right? In each of the cases, like as an air propagation or backups, uh, adding the backups, right? So in all these of them were just trying to for each state we are trying to store the V, right? So this thing is okay when we are trying to solve a problem with fixed amount of states or the number of states are very less. So suppose you are trying to solve a problem of your event space was whether if you are rolling the dice 12 times, you are rolling a dice 12 times, and what is the sum you can get, right? If that was your sample space though, so your number of samples will be between 12, that is the minimum value 12, and the maximum sum that you can get after 12 roll of dice will be 72. So you would have had 61 states, but sorry, just a minute. Okay, so as we were saying, so in each case you are trying to store the values for when you are trying to do the policy evaluation or iteration. So for a simple case like so if the sample space is, suppose sample space is rolling of dice 12 times and sum of it, so the sample space will be between 12 to 72, right? But so you are getting a 60 values, and you are trying to store each of those 61 values in some form of table. So these kind of approaches are also called tabular approaches. Why it is called tabular approaches? Because you are trying to store the the value function for each state, or action value function if it is a action state pair. So you are trying to store all of the values in some tabular form. Like if you remember the algorithms that we saw in the book or in the lecture, obviously in the book it is much preferably given. So you saw that they are storing all the values in a vector form in V or something like that. So that vector can be considered as a table, right? So each time, so when you are trying to evaluate or you want to get the best policy, you will just look at the table, you will check which value function at each state, which action is giving you the maximum value, and you are taking that, right? So that thing is your considered as your tabular approach. Now the problem is, in real world it cannot be only this small of a sample space. Sorry, just I had a very bad cold. So in a real world, sample space will be sample space for states, sorry, for states will be very large. Large in the sense, suppose it can be 2 to the power 25 states. So these amount of states can be present. These are very high number of states. So what is the problem if you want to store this amount of variables? So in today's generation, memory is not much of a problem. Memory is much cheaper than the time. So if you remember, the course that said that memory is a problem, uh, but 7 8 years back memory was a problem. These days memory is not much of a problem. You can store this amount of sample space is not much of a problem. You can store it on a memory. The main problem is your computation. So you have to compute a large number of data, right? So if you have to compute the value for each one of them, you have to spend a lot of data. So it can be a real number, it can be a integer number, but real numbers are basically are very tough to compute, right? Your fractional numbers, those are much floating point multiplication, those are much heavy occurring computation than your normal integer computations. So it's okay, the memory will be high, but the main problem lies in the computation. If you have to compute the state functions for each one of them, it is a very complex task. It will take a lot of time. So one of the solutions that is quite useful is, to solve this, two solutions came up. So two terms are very important to visualize what we are trying to do here. So I assume both of you have some machine learning background, right? At least some basic from a machine learning background. So yeah, so if you have some machine learning background, so you will know. So uh, do you remember this term in machine learning? Dimension reduction. So what happens in your typical supervised machine learning problems? You have a data set, right? So consider a data set like this. Suppose you have features x1, x2, x3, xn, right? Suppose x1000, and you have some classifier regarding it, right? So you have some y value regarding it, right? So this is your typical machine learning data set in a tabular approach, right? That is also a kind of a tabular approach, right? So if you have a data set like that, right? So what do you do here? So when you are given such a large data, do you try to just use your machine learning algorithms, be it anything like your artificial neural networks, or your not only neural networks but also your base classifiers? Do you directly apply to it, or you try to reduce your data, right? If you have such a large data with you, So at that case, you use these dimension reducibility reduction algorithms. So in those cases, you use these dimension reduction algorithms to reduce the data. So instead of so what are the criteria to reduce the data? So you generally take that how many of these dimensions, like how many of these dimension can be like features, like or say these are features basically, right? So features. So one of the main principles of dimension reducibility is that how can you combine the features so that effect on the classifier is less, right? So you basically compare that which of the features you can club together so that the effect on the classifier or the y value is same. So that is the concept we will use here. So one of the one of the thing what we will try to do, if you have such a large number of states, 10 to the power 25, we will try to club those states together. We will try to club those states together such that their effect is same on the value function, right? So that is one way of doing it. So here we are introduced to two terms: generalization and discrimination. Right. So how does these two can be defined? So let me draw a graph. Right. So in generalization, so the concept of generalization is, so suppose you have been given 10 states. Let's say you have been given these states. So your task is to make sure, so your task in that case is to get reduce the number of states. So in this case you have I have done 8 states. So suppose you generalize them to, from this 8 you say that these 3, these 3 and these 3 I will club together to form 3 new states. This is called a generalization. So basically you have generalized, so you have clubbed these 3 these 3 and these 2 to 3 new states. So this is your kind of a generalization. Now what is the discrimination? So your discrimination is sort of like this. So you see, you still have some partitioning of these states, right? So there may be criteria for partitioning of these states, but what I will try to say is that this state will differ from this state and this state. So this is how you are trying to discriminate it. So I will give you an example in tabular form how you are trying to do it. So suppose you have been given this table. Suppose you have been given this table. One, two, three, four, five, six, seven, eight. Suppose these are your 8 states and these are the value functions. Suppose these are the value functions for this one. So suppose 1, 2, 3 has a value of uh, 7, 8, 9. 4, 5, 6 has a value of uh, 2, 1.5 and 3.5, let's say. And 7, it has a value of -4 and -8. So here you can do a partition. Suppose we are trying to do a partition of generalization that if the values are between 5 to 10, they will be one group of states. Values between 0 to 4, one group of states, and values between less than 0 to -10, uh, one group of states, right? So in this kind of criteria, using this kind of criteria, you can generalize these 3 states. So you can generalize these 3 states. You can generalize these 3 states. You can generalize these 3 states, and you can generalize these 2 states. Now notice this also allows you to discriminate, right? So these are 3 discriminator factor to make sure that these 3 are different. Okay, so so when you are using a tabular approach, so suppose you are using TD0 tabular approach, like for all values, for all states you have a value function. So where should in which quadrant should the point lie? So in which quadrant should we place a tabular form, a complete tabular form? What does a complete tabular form have? Where you are typically representing each state as a separate entry, each state as a separate entry in the table. Where should we place that in this graph? Which quadrant should we place this in this graph? Suppose this is 1, 2, 3, and 4. Which quadrant should we place a TD0 tabular approach, or let's say any tabular approach? So typically you will place a TD0 tabular approach in this part, or any tabular approach in this part. So this is because In tabular approach, your discrimination is high. Every state is a separate entry, and the generalization is least. That's why. What do you typically want of a good solution in such a case so that it will be memory efficient, timeless, computation wise? What will be your typical solution? So your best solution, what you want, should lie here. So your suppose pi is the best policy you have. So your best policy should be like this. It will have high discrimination as well as high generalization. Okay, so that is the aim it should be. You want to have a policy which lies in that quadrant, top high generalization and high discrimination. But typically we can never get the best case. Okay, it is impossible in a real world to get your best solution because there will be some kind of errors. Your all the data will not be smooth as always. It will have some discrepancies and all. So it is not always able to give you that high generalization and high discrimination. Instead, what we get in most cases is this. We generally get this. So if this is v pi, so we generally get v star. Suppose here with high generalization and high discrimination, but not your typical best solution pi, where it should be. Okay, so I hope this gave you an idea what is a tabular approach and why, what is generalization and discrimination, right? Okay, okay. So let's come to the approach. What we will do now. So what we will try to do now is something called approximation, or let's say we call it value function approximation. So what typically we want to do, so what we typically were trying to do uh, in this concept of generalization and discrimination, one approach is your value function approximation. Okay. So you typically have your states and values, right? You have this long column everyone. So instead of storing it total here, you want to find a approx function corresponding to it. You want to find that. So this is typically so if you have come from your machine learning background or your deep learning background, you have your neural networks or your SVMs. Suppose you have your SVM or your ANN. They typically do the same thing. You are given a set of data. You want to find an approximate function corresponding to data. That can be linear or non-linear, right? So your artificial neural networks are generally non-linear, using those ReLU and softmax kind of things, and your SVM is currently linear, right? SVM and not SVM, yeah, SVM is kind of a linear functions, right? So that is what is your value approximation. So you have been given a set of data points and your states, you want to approximate it instead of storing all of them. So this is typically what I mean to say is that uh, so if this is your v vector for your for a particular problem, you want to find an approximation of this v vector, and it is given by generally this. So you are at a state S and you have a parameter or weight w corresponding to it. This is typically how it is done. So it is quite similar to your ANNs. So ANN, what you have? You have a set of data, signed of data, and you have your neurons. You have your hidden layer, right? You are connected to your hidden layer, and then you have your output layer, and your output layer generally gives you some output. And so basically, you are trying to compute a function. This is your function. What you are trying to compute for those data set, you are to find an approximate value such that whatever input you get and given a weight matrix, you will be able to get the values. Similarly, this is your typical value function approximation. So basically, whenever you give a state S and the corresponding weight vector you have for the all the states, you will be able to get the value function. So all thing you need to give is your state. Such a function is here exists such that you give a state and you have your parameter, that is w. You will get the value functions. Instead of storing all of them, you just store this value function, nothing more. So so previously you are storing all the value functions, right? So do we now have to store the value functions? So you are not now have to store the value function, but you have to store something. What you have to store in this case? So what you are trying to have to store in this case? Does only storing the function will happen? What does the function takes as an input? So function takes as an input the state as well as the parameters. So typically you need those parameters. So parameters or weights. So naturally this is something which you need to store. So if you are considering this as a supervised learning problem, computation of this v, what do you need actually to calculate this w and all? So what do you typically need to compute this? Right. So if you have to compute such kind of variables and functions, such kind of you need something to compute. To not compute to come to this function. What do you need basically? You need a data set, right? Supervised learning problem, you need a data set. So what is your typical data set? You have your so you typically has your state, and you need to get the return, right? So this is your typical state value matrix that you have, and using this you will try to construct the v hat s comma w. Okay, now how you are trying to uh, so our ideal, so the ideal vector was your v pi, and its place v pi s, right? So this is basically your v pi s. You have given a state and you have your v pi s. But since you can store all the v pi s, what you are trying to construct something like this: v pi s, v hat s. You are trying to construct this. Okay, fine. So what kind of your data set currently will look like? Your data set will kind of look like this. Your data set will kind of look like this. So suppose uh, you are at state st, and the return for the state will be rt plus 1 plus gamma rt plus 2. So because plus, okay, I will first write the equation, then I will come back to you. Gamma square r t plus 3 dot dot dot, or it could be st plus 1, the next one, rt plus 2 plus gamma rt plus 3 plus gamma square rt plus 4 plus dot dot dot. Okay, so this kind of data sets you will be having. Now when I said here what you have is your vpi, but typically you don't know what is vpi. So think about the in the reinforcement learning setting. So for constructing a supervised learning, what you need a data set. To construct a supervised learning, so this is your data set in RL. Okay. So to construct a supervised learning problem, you need a data set where you have your x and typically you get fx, right? So you need this kind of a data set. But the problem lies, you don't know what is fx in this case. In case it will be vpi, your optimal one. You don't know what it is. So what you have is a, in a RL setting, what you have is an agent and a environment, right? In a typical RL setting, you have this. You have an agent and you have an environment. And what you can do, endlessly you can endlessly take an action and get a reward. Action, reward, next state, right? You can typically do that in a high number of ways. Like you can continuously do that. Okay, you don't have the luxury of vpi. So that's the reason we shifted to reinforcement learning. If you understood the objective of reinforcement learning, why did you choose reinforcement learning? Because you don't have the data. You don't have the data in scenarios like this, right? You don't have a data. You have what you have is an environment. Now we are trying to go back to a supervised learning kind of setup. So how can you go back to a supervised learning data when you don't have the data? So one solution is how we are trying to do the TD0 or Monte Carlo. Suppose the Monte Carlo. What we are trying to do in a Monte Carlo? We are generating an episode, then you are calculating the reward from the back for that episode, right? And we are updating the state values according to the return. We will do the same thing here. Okay, so what we will have is a state, some state, and you will compute the return for that state based on some episode which we have generated. And similarly for all the states we will do that same. So basically what we have, we know we don't have a vpi, but we have some return which may be close or maybe away from the vpi, but at the end of the day we construct our data set like that. So you have a state and you will have the corresponding return. Remember, return is not optimal. Return is something which you have observed while exploring that episode. It is an episodic task, since, right? So it is not optimal, but since we don't have the optimal data, for us that is only the target value which we can apply in that case. So any doubt regarding this you can ask, because this was very important. What about policy? What about policy function? Will have any impact on this? Uh, so what is a policy function? So you have two functions. You have only value or you have action value, right? So action value also you can construct something like this. I will come to how action value works. So for time being, only think about value. Okay. So action values will also have something like this, where instead of only having s and t, you will also have st. Instead of having st, you will also have stat. So your typical action value functions will look like this. Your typical action value functions will be something like this. Instead of this, you will have st, at, rt plus 1, comma, gamma rt plus 2 plus gamma square rt plus 3 plus dot dot dot. The typical one, q, something stat or something like that. So typically you will be accompanied with a action statement in that case, nothing more. This is what you wanted to do, right? Yeah. So I will show you that, like how you can just define it. Nothing fancy. Like if you understand how you are creating the data set, then that's only enough for now. Okay. So that's how you are constructing a data set. Okay. So now you have constructed your data set. Okay. So now what will be your objective function? What will be your objective? Right. Every machine learning problem has an objective. So your objective in that case will be, so you have got v tau comma w, and you have your v pi, right? Your objective will be basically to reduce this gap. So we don't know how much this gap will be, but we want to reduce this gap. So what you want to do is compute the mean square error. That will be v pi s minus v hat s comma w whole square. You want to reduce this error, right? So your objective is to reduce this error. So this is your typical mean square error. Now this is for one state, so you will basically sum it for all the states. So you will sum it up for all the states. Now uh, okay, so this will give you, so your objective is to reduce this, right? So v pi you uh, don't know, but you're trying to create v hat s, and your objective is to reduce this. V pi will basically be in this case your return function, nothing more. So it will be a return, right? Just now I said. Now there is one thing. Now okay, so I will not go into the much explanation, but what typically this formula is written as something like this. You typically add a component to it called mu of s, v pi of s minus v hat s comma w whole square. Okay, so typically you have something like this. So this mu s is basically a number of times you have visited is in an episode. Okay, Nothing much fancier. It is just a probability distribution, which depends on the number of times you have visited an episode, the state in an episode. So typically, if you remember this, how your episode looks like, so you visit someone like S1, S2, S4, S1, S3, S5, then S6, S1, S7, S8, S1, right? So S1 is visited multiple times. That is what contributes to mu S, nothing new. It's a weighted sum of mean. Here, so this is your objective function. Okay, fine. This is your objective function. Now I need to. So typically, if you have done ML course, what you do with this objective function? What you do with this error? So typically, you have to inform your neural network or your how the function you are trying to. So typical objective what you have is this from here is to get an idea how far is your approx function from reality, right? So get an idea how far is your approx function from reality. Okay, so this MSE generally gives you an idea uh, how far is your approximation v hat from your data set. But now you have to improve your v hat, right? You have to improve your v hat. The improvement is basically your weights. So you have to improve your weights. So you have to make sure that this error is propagated to the weights and you update the weights based on it. Okay. So that is what your typical supervised machine learning does. So it basically takes, you have to update the weights at each case. So you propagate the error somehow backwards, which is basically called your backprop there, right? So you typically do a backprop here also. Okay, so let's do a backprop here. So your backprop will something look like this. So you are typically you do your gradient descent. So you will be doing a gradient descent here also. Wt plus 1 is equals to Wt plus alpha, your gradient of your mean square error. So your mean square error was given by sorry. So your mean square error is given by this v pi s minus v hat v hat s comma w whole square. Sorry, this will be negative. So this is how you propagate error. So this is your this symbol is basically your gradient. Gradient is basically doing a differentiation, partial differentiation. With respect to w. Right. So that is what your how you propagate your weights. Similar, it is quite similar to how you do in your artificial neural network or linear regression kind of stuff, right? Okay, so if we do a backprop on this in gradient descent on this, so this will typically look like this: wt plus 1 is equal to wt minus alpha into 2 b pi s minus s comma w, right? Now what you will write in this part? In this part you will write when you differentiate this. So notice when you are trying to differentiate this with respect to w, this doesn't depend on w, right? This typically doesn't depend on w, so it will be 0. So it will be 0 minus this depends on w, so you will basically write the gradient of w v hat s comma w, right? So if you say simplify this, this will basically come up to wt plus this negative plus 2 into alpha, this will basically be alpha because it is constant, v pi s minus gamma s comma this into delta w v hat s comma w, right? So this is your like weight updation with respect to at each step time step. This will be wt, sorry, one mistake, wt, right? So any doubt regarding this derivation, you can ask. Okay. Okay, so now let's okay, so now let's look at something called linear approximation. So before going to linear approximation, let's stick to this one more time. So let's stick with this one more time. Okay. So let me write down this again. W2 plus 1 is equal to wt plus alpha alpha let's say this is ut minus v tau st wt delta v tau st wt wt. Okay, Okay, let's come back. Yeah, one thing is that, so basically I have replaced in this case is with vpi with ut. Okay, so let u2 be some constant. Like vpi was your absolutely best optimal policy, right? You don't have uh, vpi is not vt, so no, sorry okay, if there is some issue I will rewrite it. Okay, so this is your u ut. Okay, this is u. Okay, so what I'm saying is that vby is absolute best. Okay, you don't have that. You don't have that when you when you're trying to compute this. Okay, so what you have something called ut is basically a, let's say, noise corrupted version of vpi. Let's say it's a noise corrupted version of vpi. We will come to what can be the typical values of ut. Okay, let's say this is a noise corrupted version of vpi. Okay, fine. Now let's come to first one, Monte Carlo. Okay, so what will happen in Monte Carlo? Weight update. So suppose you are trying to approximate the Monte Carlo solution. You want to approximate the Monte Carlo value function. So what will be the typical weight updation in that case? Wt plus 1 is equals to Wt plus alpha. What it will be in Monte Carlo? What will be in Monte Carlo? Monte Carlo, it will basically be your return, gt. Return and timestamp t, st, wt, delta, delta wt, v tau, st, wt. Right? In Monte Carlo, this will be your ut. Right? What is gt? gt is basically return at time t, time step t. Now also, what is gt? Also, what is a return? Come on, you know the definition. What is a return? Return is basically an estimation of your value function, right? Return is basically an estimation of your value function. So you can replace that value function with your estimation. So gt is actually an estimation of vpi, right? Typically it's an estimation of vpi, right? So you can replace the vpi with jt, and you can compute the entire Monte Carlo sequence with this kind of weight operation, and you will get a very nice function. Okay, and this is your typical formula to do it. So you can look at the book and get the algorithm, but this is typically the algorithm is quite simple, like quite the same. Just you are typically doing the weight updation in this case. Instead of updating the value function at each case, you will typically update the weight function. Okay, so this is your Monte Carlo. This part is clear. This Monte Carlo update. Okay. Now this will be a curveball for you. What about TD0? What will be the update situation? What will be the update situation in case of a TD0? Wt plus 1 is equals to Wt plus alpha. What will be in this case of ut? What it will be? It will be your one step look ahead return, right? It will be one step look ahead return. What will be our typical one step return is r t plus 1 plus gamma v tau st plus 1 comma w minus V tau, V hat, ST, WT, and then your gradient coefficient. Right. This should be the update rule in case of TD lambda, TD zero. Do you agree with this? So do you agree with the statement? This would be the output. Yeah. Except there is one mistake. What is the mistake? So this is typically your. If I consider this equation and this equation, so this is typically your UT, right? This is typically your UT, right? Now can you apply can you apply gradient descent on this and can assume it will be zero? Can you do a partial differentiation of this with respect to WT and assume that this part will be zero? Right, so this is your WT. Right, so typically this will not work. Here gradient descent will not work, will not give you correct result, because this is not an unbiased estimate of. Here this part is not an unbiased estimate of V pi. This is not an unbiased estimate of V pi. What you are trying to do is you are trying to use the previous value to update to update the one step look ahead return, to get the one step look ahead return, right? So your V hat, so this UT depends on your V hat ST plus 1 WT. So when you are typically trying to apply the partial differentiation operator, like your gradient descent, so this part will not come down to zero, rather it will have some value because you have the V hat portion and that, right? So this is not an unbiased estimate of V pi. Clear? So this, although we use this update rule, but we call this semi gradient, not a full gradient. While Monte Carlo you are using a full gradient operation, here you are not using a full gradient operation, instead you are using a semi gradient operation. Update rule will be same, but it is not the minima. So update rule is basically typically trying to find out the minima, so it is not the minima. So the error will not be absolute minimum, you are not going to find the objective, but it somehow gets the result. So if you look at the objective, this will somehow give you the objective of finding a fixed value. Semi gradient will take longer time to converge. Okay, I am not sure whether it will take longer time to converge, but it will converge. Okay, it will converge. See, that typically the problem lies in uh, it will converge, and at the end of the day it will converge, but I'm not sure it will be faster or slower. I'm not sure, I have to check. Okay, so please find out a Google search or something and do it. Okay, so this is our semi-gradient method which we could talk about. Now let's come to the next part, which is your linear approximation. So suppose you have a grid like this. So again we will come back to the concept of generalization. Okay, suppose you have a grid like this. Suppose you have a 4 cross 4 grid. Okay, you have a 4 cross 4 grid, and suppose you are currently at this. So remember that ice walk on ice problem or something like that, uh, where your goal is to reach the from one corner to the other without flow, without ice lake problem, without falling into the lake. You only can walk on the ice. So similarly, look, some kind of a grid problem you have. Okay. Okay. So now you find out that the value function, uh, value function depends on the sum of x and y coordinate. Suppose this is x and this is y. So let's say you find out the value function at some point depends on the sum of your x and y coordinate, some average sum of x and y coordinate. This is a typical example of your linear approximation. So you can approximate the linearly your value function in that case. Okay. So typically by linear approximation, what we mean is that some value function at state S and parameter W, weight parameter W, is given as WT xs. This is typically how you represent your value function in a linear approximation setup. Right, so this is how. So what is xs? Xs is your set of features. Is basically your set of features. Now let me give you an example of how features work. So suppose if this is your this is your problem setup where you have 16 grids. So what you will have typically in a tabular approach. So you will have a sorry. So you will typically have a like something like this, state and value, right? You will have something like this, and you will have 16 entries here. You will have simply 16 entries, something like that, right? So if you want to accommodate this into something like this, what it will be? So it will look something like this. Suppose you want to have value of state 1 W. What it will typically be is you will have your weight matrix W. Suppose state 1 has a value function of 6, and what will xs in that case be? An identity matrix such that it will be 1 followed by 16 zeros, so 15 zeros. So each so for state 1 it will be this, state 2 it will be this one only 1, state 3 will be this one will be 1, and so on, right? So that is how your typical tabular approach from will look when you are trying to linearly approximate it. So is this part clear? How I am climbing from this to this for a tabular method? For a tabular method, how I am climbing this to this? So you will typically, so this typically your so this weight wt, this weight vector will be in that case your entire value in the table, and your this one will basically be 1000 for first state. For second state will be second vector will be 0, or less all second vector will be 1, less will be 0, and so on, right? So first tell me that whether this part is clear, this moving from a tabular approach to this approach, linear approximation. Then I will move. Okay. So now I want to. So our goal is what? Our goal is linear approximation. Our also goal is to generalize it. Right. What we'll generally do in a generalization? We'll basically club few. So in generalization, what you will try to do is club few states. Suppose we club state. Suppose we generalize state 6 and 8. So in that case, what will happen is the weight vector. Let me just use a very small one. Okay, that will be a very big table to represent for me. Suppose we try to generalize 1 and 4. Okay, so in that case, this identity vector will look something like this: 1 0 0 1 and rest zeros. Okay, so that is how you are generalizing it. You are saying that these two weights will be these two states will be same. So in that case, whenever you are trying to either select 1 or select 4, you will basically use 1001 as your identity vector. So you will have, yeah, so you will basically have one less state, right? So previously you have 16, now you'll be using only 15 states. For 1 or 4, you will be using 1001 as an identity matrix. Okay, so that is how you generalize. That is the simple way you are trying to generalize it. Okay. Now we'll come to two types of okay. Just give me a second. Now you'll typically I will give you a small description of two of this generation technique: coarse coding and tile coding. So what is coarse coding and tile coding? So suppose you have this big pond. Suppose you have this big pond, and there is a fish in there, and the fish typically moves from one coordinate to another coordinate. Okay, and that defines a state. So you have a fish here. Okay, it may look like a fish, but whatever. Okay, so you have a fish here. It moves in a pond from one place to another, and typically the position it is at, it is considered as a state, and so it is a very big state. Okay, so it can be in a very big pond. So now you have to reduce the number of states. So what you can do is that you can create some boundaries. Okay. You can create some boundaries, and whenever the fish is in some one of the boundaries, will define that state. Okay, so that is how you are trying to generalize the states. So it may so happen that only generalization like this will not give you a correct result, will not typically give you a correct result. Okay, so one method is to have overlapping such circles or overlapping such boundaries. So one method will be like this. Okay, so you have this kind of overlapping boundaries. So the fish in at any point can have in such overlapping boundaries. Okay, so you have, in this case you have, it is inside three overlapping boundaries. It is inside this, is it inside this, and it is inside this. So whenever you are trying to estimate a value function or something like this, you will have basically uh, like, so suppose there are 7 circles, so you will basically update 1 0 0 1 0 1, something like this. So some kind of vectors like this you will use and update the weights. You will typically get the value like that. Okay, now another simple headache is how many such overlapping circles you need, whether less will be good, whether more will be good, whether having asymmetric circles will be good, like circles of different size, varying size will be good. There is a experiment you will see on the book they have done to understand what kind of generalization is good for function and all. You can go through it and check. Okay, so this is called coarse coding. Now, the name coding just says that how you are trying to identify state, right? That is why it is called coding. What about overlapping region with more than two? Nothing, not a problem. Okay, so okay. If you want to see that diagram, I can show you, and what is good or what is bad. So give me 1 minute. So is it visible? So this is something called nano generalization. You see, there are only very few overlapping circles. This is called broader generalization, and this is called asymmetric generalization. Okay, so this one has much more overlapping circles. Now typically this is the function you are trying to approximate. See, this gray one is the thing you want to approximate. This is using narrow features, this is using medium features, and this is using broad features. Okay, this is your narrow, broad, and asymmetric. Narrow, medium, broad. Sorry, asymmetric is not there. So suppose there are three kinds of one is there. Okay. Now we're trying to approximate it. Now see which one is getting closer result very faster, right? They are doing the experiments. So this one after 40 is somewhat good. This one is also somewhat good, but there are errors outside. So typically, if you look at this one is quite close. This one is quite close. After a certain time, this one is giving a best features. This one is also giving a best features. So you have to do this kind of experiments to check which one is good for you. Yeah, you can read this part and do it, but this is how your typical approximation behaves with narrow features, medium features, or broad features. Okay, so in tile coding, it's quite similar to your. It's a special case of coarse coding, but it goes something like this. Suppose this is a 4x4 grid, and your fish is here. What you will do is you can use a tile above it, like this, and enforce over it. Okay, so you can use multiple tiles over it, and then you choose those tiles, those coordinates in which the fish is present in all of those tiles, and then you create a same kind of identity matrix on it, and then you multiply it, you get the weight. With the weight you get the value function. Okay, this is another kind of approximation. So typically in this case, your fish lies in two quadrants. Oh, okay, let me use a different color. That will be better. So your fish is typically in this quadrant, and this quadrant, and you update the feature vectors for these two quadrants, and typically you will get it. Naturally you will get it. Okay, this is your coarse coding and tile coding. So what else is left? Yeah, tell me. Which one is preferred? See, each one of have them their own use cases. Right. Which one is preferred in mean coarse coding or tile coding? So if you can fit it in a tiling kind of structure, then obviously you will use the tile coding. No, but all of them, all everything cannot be envisioned like that. Which one is the best approximation? There is no such data given in the book. So there is no such data given in the book. We have to search it. But the effect of tile you can get, like if you are using one tile, the error will be much more than when you are using something called 50 tiles. There is this one result in the book is there. Okay, but tile coding is a specific case of coarse code. Okay, coarse coding is your top. What else was there? Linear approximation, tile coding. LSTDQ, right? So let's quickly do it. LSTDQ. LSTD and LSTDQ. So at TD we have already shown that. We have already shown for TD that I have already shown that. So I have already shown for LSTD that it is not a full gradient. It is a semi gradient kind of setup we have, because you are not using an unbiased estimate of return. You are using basically a biased rate of return. So for weight update. So typically your weight update formula, if you, in case of a linear regression, linear in linear. Okay, so okay, one thing I forgot. Okay, let me do that before. So Monte Carlo linear approx. What will be the weight update? So your typical linear weight update was Wt plus 1 is equals to Wt plus alpha Gt minus V hat is W V S T W. Right, this was your typically Monte Carlo Monte Carlo update. So in case of linear approximation, what will be this value? Delta, like uh, not delta, it is your gradient V tau STW. What it will be? What it will be? It will be a gradient on. It will be a gradient on WTX, W transport X, right? Right. So it will be typically XS, right? So you can replace this equation like this. Wt plus 1 is equals to Wt plus gamma G of t minus V gamma St Wt x of St. Right. So this is your update rule for Monte Carlo linear approx. So this one is only available when you are using linear approximation, not all cases, but only for linear approximation. Now your typical LSTDQ setup in linear setup. Sorry. Your update rule will be something like this: Wt1 plus Wt plus 1 Wt plus alpha or t plus 1 plus gamma W Okay, let me write the previous one, then we will go. Sorry. Gamma V hat is dash T W T minus V hat is T W T sorry x of s. So, since the operator is now linear, we can replace it x of s, and also we can replace this one. We can replace this one and this one with the linear formula wt plus alpha rt plus 1 plus sorry w t tau x of t plus 1 minus w2t xt xt. And if I simplify it, I'm just writing down the formulas. Okay, wt plus alpha, so I will multiply it here, rt plus 1 xt plus, sorry, it will be, so this is some linear algebra, nothing more, minus x of t minus x of t xt minus gamma xt plus 1 transpose wt. wt. Okay. Okay, so this is your typically update rule. So if you have confusions of how I reach from this to this, is basically just multiplying it here and just doing the stuff out. Nothing more, nothing fancy. It's just simple linear algebra. If you follow the equation, it is same. Okay. Now it has two parts. This part, so it has two part now. This part and this part. So this is typically written as wt plus alpha b minus awt, where a is equal to typically an estimate of xt minus gamma xt plus 1 transpose and b is equals to rt plus 1 xt. Okay, so if you have to do the weight updates, what you have here, what you need is this, what you need is this to compute, and to compute this what you need is these estimates. So how to calculate estimates? The more you sample, the more you get the estimates. In sampling, in this sense, collecting your data, more data. So as and when you do the more sampling with communicate more between the agent, communicates more with the environment, you will typically get a action reward kind of pairs for this, and you will be able to compute this value. And to get the weights, so typically what you will want, we will want to continue as long as this error term becomes 0. So that is b is equal to b minus a w td is equals to 0. That is when it is converging. So typically your weight matrix will be something like this. You want to find this. This is what you want to find. This will be your weight matrix final, right? So basically computing this to be 0, you want this to be as close as possible, or this to be 0. So you have to compute this WTD. Okay, this is what is your LSTD. So in LSTD you compute this WTD and do your typical weight update for your TD0 algorithm, or any TD0, TD lambda, anything. So you can do that and continue. So it is, if it was TD lambda, so if it was TD lambda instead of TD0, the only difference will be here you will would have been included a lambda term, nothing more. Okay. Okay, so that was this week's wrap up. So I understand the thing that was explained in class was much more typically difficult than this, but this was a shorter version of what was being said, this LSTD and all. So your LSTD algorithm is basically at the end of the day this. So the more you sample, and you have to compute this part. You have to you will get A and B by sampling, and you compute this RTD. Okay. So let's now solve this week's questions. So this is question number 1. Is the problem of non-stationary target an issue when using Monte Carlo as targets? Is the problem of non-stationary targets an issue when using Monte Carlo returns as targets? So the answer is no. Because typically when you are using a Monte Carlo target, answer is no. So when you are using a Monte Carlo returns as target, you know beforehand that it is a stationary target. Hence, values do not evolve as parameters change. Right. So when you are using Monte Carlo, you know very well from the beginning that you don't, the targets are stationary. So that's not a problem. Okay. So let's go to the next one. In a parameterized representation of value function, we use a feature which acts as a counter of some concept in the environment, number of cans the robot has collected, for example. Does such a feature used for representing state space leads to a violation of Markov property? So in a parameterized representation of value function, we use a feature which acts as a counter of some concept in the environment, number of cans the robot has collected, for example. Do such a property used for representing state space leads to a violation of Markovian property? So the answer is no. So it does not violate. So when you are generalizing, so think about it. The question basically says when we are generalizing states, are we violating MDP properties? That is what the question asks. Okay. The answer is no. Because we are generalizing or stacking up only those states which are related. Okay. The probability distribution and all those are related. Those are not, we are not trying to. We are only generalizing a subset of it to it. And the goal is remains the same, that it does not disturb the uh, Markovian property. Okay. So the goal remains the same, that it doesn't disturb the balance in the system. Okay, so let's go on to the next one. Which of the following will affect generalization when using tile coding method? Modify the number of tiles in each tile, modify number of tiles, modify the number of tiles in each tile, assuming the range covered among each dimension, modify the number of tiles, modify the size of the tiles, modify the shape of the tiles. What will be the answer? Any guess? Only B. B is correct. I'm not doubting. B is correct, but only B. Actually, all of them. Yeah, it's actually all of them because you have a tile like this. Now you are typically using another tile like this, right? Now these two are of different size and shape. Okay, so it will affect the generalization. Now I don't know whether it will increase or decrease, but it will affect somehow. Also remember, tiling is a special course coding. So as I saw as you viewed the example which uh, I displayed you a few moments back, you saw that how the shape and size of the courses circles affect your generalization property. How someone does it faster, someone less error prone, and all. Right. So the same properties applies here because tiling is a special case of it. So correct answer is all of the above. Okay, so let's go to the next one. So for a particular MDP, suppose you use function approximation and using the gradient descent approach converts to the value function that is uh, global optimum. Is the value function the same in general as the true value function of MDP? So what does the statement mean? This question mean? So typically what this question means that you find out something. So suppose this is your v pi. Okay, and you have your v hat. Okay, you use function approximation and using gradient descent you come close to something, you find a minima, and this is your v pi v hat star star. Okay, so they are saying is these and these equal. They are saying is these and these equal, that they mean to say is both the value functions are same. Is both value functions are same. I mean, are these three same? V star, V pi, V hat star, and V star. Are they same? What's your guess? Are these three same? Yeah, because V hat was the initial one, and after doing all sorts of linear approximation over several rounds and all, after several batches and all, you come to V hat star. Right? You come to V hat star. Now the question says whether V pi and V hat star are same or not. The answer is no. Maybe, but maybe not also. It may be same, but it also may not be same. In some cases it may be same. It may some cases it may not be same. So the answer is actually no, because typically when you are trying to reduce using means square, let's not look at mean square error. So suppose you have this thing v pi, and you have you have gt, right? You have the gt from typically uh, your Monte Carlo. Suppose you have used Monte Carlo, right? So is GT and VPI same? No, because GT was a unbiased approximation of VPI, right? A one unbiased estimation of VPI. Similarly, here also, instead of GT, you have V hat star, right? And V hat star will maybe close, very close to VPI, but it is not VPI in most of the cases. Sometimes you may get VPI if your luck is very good, or if the function is not that highly complicated function, then you can get it. But in most cases, you will not. These two all will not be same. Okay. Okay, let's come to the next one. Which of the following methods would benefit from normalizing the magnitude of basis functions? Online gradient descent, linear gradient descent SARSA, uh, LSPI, LSPI, and none of the above. So typically, you are when you are doing some kind of gradient descent one. So basis, what is a basis? Basis is basically your identity one, not identity but feature vectors. Identity is a very easy way to represent it, but typically these are your feature vectors. Typically, when you are doing gradient descent, it is good to normalize because it will be very less computational effective in that case. So typically A and B are will benefit from the gradient descent, like normalizing the value, because typically your feature vectors will reduce. Yeah, no, normalization and variance are normalization and variance. Yeah, no, it will reduce the variance, kind of. Yeah, true. It will reduce the variance. Yeah, normalization will reduce the variance. LSPI is different because LSPI is basically your. So I haven't discussed the LSPI, but LSPI is your policy improvement, right? In policy improvement, what you do. So LSTD was your policy evaluation, and LSPI in policy improvement, what you do. You basically solve a system of equations. So that is not gradient descent. So these two will be the one. Okay. So suppose you have individual vectors phi I si infill features. Okay, yeah. So what I was telling is, so far what I was doing is xs. So similarly, you can have feature vectors x of s comma a when you are when you are doing a q learning sort of, when you are trying to use a action value pairs. So you can just replace, you can have a similarly feature vectors of both s and a and do it. So what this question says is, suppose the individual features S and A used in the representation of action value functions are non-linear functions of S and A. Non-linear functions of S and A. Okay. Is it possible to do LSTDQ in such a scenario? What do you think? So, so when you are discussing LSTD, something like that, or linear approximation, what is linear? Weights or features? So when you are discussing all these linear approximation method, what is linear? Weights or features? So typically your weights are linear. So your weights are linear. So that's why you are trying. You can approximate the weights vectors using simple addition and all. Okay. So so these action value functions, even if they are non-linear, it is not going to be an issue. You are typically using the delta function on weights, based on weights. You're using the gradient descent on weights, not your feature vectors. So your weights are the one that are linear. So this is not going to be a problem. You can use non-linear S and A feature vectors. That's not an issue. Understand this? This question is clear. Why we can use non-linear S and A? Because the linearity operator gradient descent, you are applying on your weight vectors, you not on your feature vectors. So that is not going to be an issue. But linear approx will work. Yeah, linear approx. I mean, on whom on whom you are using the linear operator gradient descent? On whom are you operating? You are operating on W. Your S and A are functions which are non-linear, but it depends on S and A, not on W. Right? It doesn't depends on W. Your feature vector doesn't depend on W. So it doesn't matter whether they are linear or not. Your linearity stops and starts with weights, right? So that's why it is not going to be an issue. So linear approx will work in this case. What basically you will do? So so uh, 1 minute. Give me a second. Right. So this is what you have, right? This is what you have, right? Excess. So after differentiation, after applying it on this WT excess, so this is what you get. So here excess is linear or non-linear, that is not going to be an issue, right? This is the linearity operator you are applying. This is the linearity operator you are applying, and it depends on W. So since W is linear, that is not issue. Okay. Okay. So let's go to the next one. Which of the following statements about LSTD and LSTDQ are correct? So LSTD was state value function, right? LSTDQ was action value function, right? Both LSTD and LSTDQ can reuse samples. No, they cannot reuse samples. They are once the sample is done, you generate a new sample. That's how you will get new data. And both LSTD and LSTDQ can be used along with tabular representation of value function. True. You can use it because tabular representation is a specific case of your linear approximation. Okay. Because this tabular representation is a special case of linear approx. Okay, so let's come to this one. Uh, Consider the 5-state random walk task described in the book. There are 5 states, S1, S2, S5 in a row, and two action is S1, S2, S3, S4, S5 with two actions each. Either you can go left and right. There are two terminal state at each end. So uh, if you terminate on the right, you get +1. If you terminate on the left, you get -1. And a reward of 0 for all transition states. If you go from this to this, you will get a 0. In designing a linear approximator function, what is the least number of states features required to represent the value of equiprobable policy? So how many states you will require in this case? How many states you will require? Come on, this is easy. So you have been given some of the states. If you move between this and this, you will get 0 result. If you go this side, you will get -1. If you go this side, you get +1. So how many states are required to represent this problem? Why 2? No, you don't require 2. Left and right are actions, not states. You will require only one state. Yes. So if you go this side, you will get 0. You will get -1. You will go this side, you get +1. Nothing more. For the others, it will just basically loop on this. Only one will be enough, because the movement between the states is 0. So you can just consider all of them to be one state. Okay, so that was the last one. Thank you for joining. You can ask any question, or we will meet again next week at the same time. Okay, thank you for joining.